Okay, so welcome everybody. If you're supposed to be at DevNation, you're in the right place. And title of the talk is Hadoop and Beyond Architectural Considerations for Scalable Storage for Big Data. That was the title when I submitted the abstract. I've done some mild hijacking of the topic in the middle here, you'll see. But I'm really going to stress a little bit the and beyond part because I want to talk some about where Hadoop is going, not just where it's been. And so there's a fair amount of that toward the end of the talk. It's really divided into three parts. First part, I'm going to talk some about GlusterFS, which is a distributed file system that forms the basis for a product from Red Hat called Red Hat Storage. We've done a plugin for Hadoop for that allows you to run Hadoop workloads directly on the Red Hat Storage cluster or the Gluster file system cluster. So I'll talk some about the overview of Gluster itself, then some about how our file system plugin works and how you would run Hadoop on that. But then I'm going to switch gears a little bit and go from there for some of the directions that Hadoop is taking that's happening in big data processing and how they probably change the way compute and data interact for big data. So I'm Scott McClellan. I'm in the CTO office at Red Hat. I run the big data engineering team. Been there approximately 2 years. I feel non-ashamed to say that I'm still very excited about being at Red Hat. That I think it's kind of like the little engine that could company, especially if you're coming from a big company like HP or a much bigger company like HP, which I will not bother to disparage in this talk. But no, I'm just kidding. But Red Hat has a definite can-do attitude, and that's really cool. And so we've been really building up our team and tried to broaden and widen our initiatives around big data, and that's been exciting. I was at HP for 27 years, which the main point there is that I'm old. But I was the VP of engineering and CTO and founder of our cloud group at HP, CTO of hyperscale computing, CTO of business critical computing, and CTO of high performance computing, and worked on a proprietary operating system called MPE, which is older than anybody in the room except me probably. So anyway, most people won't know what MPE is, except Jeff, he worked on it too. So sort of big animal picture, Red Hat Storage. This is going to be probably the only time I really talk about the product Red Hat Storage, but it's a package that's it's approximately equal to a supported and tested package of the Gluster technology, the RHEL, Red Hat Enterprise Linux operating system with the XFS add-on, plus a management console, plus now with our solution plugin for Hadoop. That's packaged together, and we offer subscription support services like Red Hat always does around open source technologies around that as a product. Gluster itself is the upstream, is the distributed technology, file system technology, and there's an upstream developer community called gluster.org that around Gluster. And then downstream of that exists the Red Hat Storage product. And this not being a product talk, that's pretty much all I'm going to say about Red Hat Storage, except for in a couple of places I'll point out a relevant difference here or there between Gluster, the upstream technology, and Red Hat Storage, the downstream technology. So a super brief overview of Gluster. It's, at a high level, it's a distributed scale-out network-attached storage file system. It's commonly used for storing very large quantities of long-tail data, such as pictures, videos, user data, log files, mostly not completely static, but data that tends to not change super frequently. It's an excellent storage repository for that, which coincidentally is the same kind of data that people are often processing when they do big data applications. So it is commonly used for storing the same types of data that people process in big data. GlusterFS was originally developed by Gluster Inc., which was acquired by Red Hat in 2011. It has a few high-level attributes. It runs on pure commodity hardware. Kind of a main emphasis behind, or driving force behind Gluster is that it doesn't require anything exotic in the hardware layer. It could run on anything from a thinly provisioned storage server, a server that has very little storage, to a server that has tons of storage. Gluster doesn't care, but that does affect the economics of the solution, because if the individual storage nodes have much more storage, then the aggregated storage pool will obviously have more storage without having to have more nodes. So it affects the ratios of scaling on the two axes to deploy it on servers with more storage. But there is no requirement that that these be exotic storage servers in any way. Pure commodity storage servers will work. They're offered by many manufacturers. I'll show you an example in a minute. Data in Gluster is stored as Linux files in pick your favorite Linux file system. The Red Hat storage product is built around supporting stored in XFS, but that's not a requirement of Gluster. It can be stored in ext3 or ext4 or BTRFS or pretty much any Linux file system. There is a requirement that that Linux file system support extended attributes, because Gluster keeps a lot of metadata in the extended attributes. So if you found a file system that didn't have support for extended attributes, it'd be difficult to get Gluster to run on that. Data is distributed around the cluster of nodes in a deterministic fashion using an elastic hashing algorithm. And that algorithm can rebalance the data based on capacity or on failure events in the cluster. And so it's got a self-healing daemon that can trigger a self-healing process. And also if you're and the elastic, I'll say more about this later, so I'll just not say it now. The clients could access the data in a Gluster storage cluster via NFS or Samba CIFS, or the native Gluster client, or through a fuse mount, or through an API we support that's Swift compatible, so you can treat the storage in Gluster as object storage, or now with our plugin, you could access the data in Red Hat storage as if it was Hadoop through the Hadoop file system API, and that's essentially jumping ahead what our plugin does. So bottom line, Gluster will run on just about anything. A typical Hadoop node, it would run on that, which this is an example from the HP reference architecture for running Hadoop of a 2U server that has something like 48 to 96 gigabytes of memory and typically 12 drives in this 2U chassis. Gluster runs fine on something like that, and Hadoop prefers a node like that. Gluster is often deployed in production on a node more like this, which is again taken from the HP reference architecture for Red Hat storage. And this is an HP SL 4540 in 2x25 mode, which means it has two trays in the chassis that have 25 disks each. So in 4.3 units of rack space, you have 50 disks here. So you can see if you deploy Gluster on something like that, you get a lot more storage capacity in the same sort of physical footprint. This is very dense from a storage perspective. When you're forming a Gluster cluster, basically the way it works, well, I'll define a few terms first. The first one is one you can easily get tongue-tied around, but there's this notion of a brick. And essentially a brick at the end of the day defines the storage assigned to a given volume on a given node. A volume is a GlusterFS abstraction. It provides management abstraction for a chunk of storage out of your total pool. So you could divide your pool of storage into multiple volumes. It also provides some isolation because they end up being separate namespaces if you want them to be separate. Well, they are separate namespaces. So you can have different constituents sharing a storage pool with different namespaces carved out of that pool that can be managed separately, and that's a volume abstraction. And we have the overall, all of the aggregated storage, or all the nodes when they form together, they form what's called a trusted storage pool. And so that's the collection of nodes that have established peering relationships with each other. In Gluster, all the nodes are peers, so there is no hierarchy. There's no masters and no slaves, so they're equals. The command to establish the cluster is even called peer, peer probe. So any node one node would probe another node to become its peer. So that's the way that they're invited to join the cluster. And then use a peer status command to check the status of the nodes. Again, it's designed for commodity servers, but the point I'm trying to make here is that that GlusterFS has no strict requirement that all the servers be the same. Typically, the clusters would be pretty homogeneous. similar configurations, but you could deal with differences like some servers with lots of storage and some with less by managing, there's capabilities to do that by defining the bricks differently, et cetera, for those different nodes with different storage configurations. You put Linux on all the nodes in the trusted storage pool, and you put Gluster itself on all the nodes in the storage pool. And when I say you put Gluster on it, that means you're running both the client part of Gluster and the server part. So within the trusted storage pool, every node is both a client and a server. And of course, you can have servers to access data that's within that trusted storage pool from anywhere outside of Gluster. You would only need to run the client side of the Gluster stack, or even just run an NFS client. You don't even necessarily have to install anything. GlusterFS does not require local storage on the nodes to be set up with RAID or LVM. This is one of the places where I'll point out a difference. Red Hat Storage product is certified that the nodes the storage would be configured in RAID 6 with logical volumes, and that's the Red Hat supported configuration, but not a requirement of Gluster. Oops, I go the right way. Okay, so essentially, if you're wanting to form, I confused myself because this is showing me one screen ahead, and then I thought I've already seen that screen. Anyway, so like a simple, to establish a cluster, you could do this is a super simple example. If you just had 10 nodes, you wanted to put them in a storage pool, you could just do a for loop from 2 to 10 run this on node 1 and invite the other 10 nodes to join, and then wait a little while and execute a peer status command to verify that they've all joined. The peer status output looks something like this, where it's going to give you a whole list of nodes that it knows about, and it'll have a peer in cluster status and a connected adjective next to it that says that it's actually successfully joined the cluster. As a simple example, if you had 6 nodes, cleverly named node 1 through 6, and you wanted to have one volume, cleverly named volume 1, and there was just going to be one brick on each node called brick 1. I wasn't being very clever here. And you wanted to have 3 directories in each, just hypothetically, you just had 3 directories, D1 through 3, and 3 files in each directory. That's the simple setup. You could do a create, Gluster volume create, give it the name of the volume, volume 1, tell it what replica count you wanted. In this case, we were saying we wanted each thing to be 2 replicas of all the storage in there. And then give it a list of all the node and brick pairs that are in that volume. So this command can get long, but that's how you would establish a volume across a big cluster. And this is taking lots of defaults. Later I'll talk about Gluster translators, and there is a way to hand edit the volume specification file to change which translators are parameters to the translators. But here, this would be a distributed replicated volume with a replica count of 2. And all the rest of the stuff would be at default with that command. That would end up with a cluster that had a single volume stretched across the whole cluster. Associated with that volume the storage associated with that volume on each one would just be brick 1. And then when you put the files in there for the 3 directories, D1 through D3, and files 1 through 3, you might end up with a distribution like this where directory 1 has the files in directory 1 that are on node 1 are file 1 and file 3. I don't know why I said 13. This is because I changed my naming convention. Just think of that as file 1 and file 3. And since node 2 is a replica of node 1, you'd see the same 2 files in directory D1 on node 1 and node 2. Does that make sense to people? Directory node 5 and 6, which are replica pairs. In this particular example of how the hashing algorithm worked, which I just made up, none of the files would end up on node 5 and 6. 2 of them would end up on node 1 and 2, and 1 in node 3. And then D3, they split, and directory 2, they split evenly. File 3 was here, file 1 was there, and file 2 was there. But anyway, you get the idea that elastic hashing would distribute the files across the cluster based on a hashing algorithm, and would attempt to also level the capacity of storage associated with those files to achieve some leveling across the cluster. So the Gluster's elastic hashing means that there's no distributed or centralized metadata for the file system like there is in the case of Hadoop. Hadoop has a name node which has essentially a database that keeps track of all the files that are in a Hadoop cluster and where the blocks for those files are distributed. So that name node is a separate server and it's considered a master. So contrasting Hadoop HDFS to GlusterFS, Hadoop is a master-slave architecture with centralized metadata. Gluster is a peer, no master slaves and no centralized metadata. Again, there are the directories for every file. All the directories are on all the nodes. So every node knows about the directory namespace, but not all the files are on every node. The files are scattered about based on the hashing algorithm. Let's see. So it uses the hashing algorithm to determine file placement. If you were to like rename the file, Gluster doesn't burden the rename with copying all that data to. So the rename, the new name could cause it to land on a different node. By the hashing algorithm, Gluster would not copy the data when you did the rename. Instead, it would put a pointer in there that says you came here looking for the data, but it's been renamed. You came to the place where the new name is looking for the data, but it's actually in its old location because it hasn't been moved yet. And then a background process would move the data later as part of a kind of a cleanup or rebalancing operation. So it's not like a rename takes as long as it would take to move the data if you renamed it to something that would cause it to be on a different node. Elastic refers to the ability to add and delete nodes from the cluster without screwing up the hash placement algorithm. So it's based on an algorithm that supports changing the size of the number of hash buckets, essentially. So it has to be elastic to support that. Gluster has this concept of a translator, which is actually a simple concept, which is if you take all the stuff you could do to a file and you break each thing down to its simplest form, like into a discrete operation, and you create a translator for every discrete operation, then the way you stack up those translators will define the behavior and the operations and features of a given whatever thing is going through that translator stack. So we associate translator stacks with volumes. So when you define every volume can have its own translator stack. Translator stacks don't have to be all the same. So the behavior and characteristics of every volume can be customized by having custom translator stacks for those volumes. Does that kind of make sense to people? There's a lot of translators, and I'm not going to come even close to attempting to explain it. But if this is the client side, and this is the server side, remember in a trusted storage pool, every node is a client and a server. But then basically there are debug translators that can appear on either the client or the server side of the stack that allow you to collect statistics and stuff on on what's happening on the I/O path, and they could either be in the path or not in the path. So that's an example of customizing the stack. There's a number of performance translators on both sides of the stack for prefetching and doing quick read and I/O caching and read ahead and read behind that could be on either side in some cases. Then there's there's a protocol type of translator that says, when you're making essentially the RPC to go from perhaps one node where your read request is happening to another node where the read is going to be satisfied because the data is actually on a different node. This is an RPC mechanism, and there's different protocols, stacks supported for different types of RPCs. Then there's the debugging one appearing again. This has to do with a marker for, well, this one down here has to do with setting quotas, and this one up here has to do with some other efficiency that I can't remember off the top of my head. There's another performance one, there's a locking one. At the very bottom, this is the part I wanted to point out, is the storage translator. And by default, the normal bottom of a Gluster stack is a POSIX file system, which is how then ext3 or XFS or any other file system could sit underneath Gluster. However, you could put a Berkeley database, a BDB database under here, and there is a storage translator to persist the data in a BDB database. In theory, this could be a NoSQL database or something else. But the typical way Gluster's used, the storage underneath it is a POSIX file system. It doesn't have to be because of the flexibility of the translator mechanism. Does it make sense? Okay, so we've created a plugin for Hadoop, a Hadoop plugin for Gluster. The way it works is the file system for Hadoop has always, since pretty much the beginning of time, been pluggable. People that ran Hadoop have always wanted to be able to run it on like their laptop, which is not a cluster. So if you want, so it turns out that HDFS is an implementation of the Hadoop file system API, but there's another implementation called the raw local file system that when you use the raw local file system instead of HDFS, then you can run Hadoop on something that just has a local file system and is not a cluster. So Hadoop's always had this architecture, okay? And so that would allow you to, say, run MapReduce jobs on your laptop, and they would, you know, make Hadoop file system API calls, but there's no Hadoop distributed file system running on your single laptop node. The raw local file system is satisfying the reads and writes through that plugin that's existed for Hadoop for a long time. Essentially, what we did is we started with that raw local file system plugin and extended it, or basically override any methods within that object class that needed Gluster-specific code, which turns out to be very few of them, because Gluster is itself a POSIX-compliant file system, so there's not very many places where the raw local file system needs to do something different for Gluster than it does for normal file systems locally. An example of a place where it's different is when you're trying to look up locality information. If you're running on a single local file system and you make a get file block locations call, you don't have to look up where the file is. It's in the only node you have. In Gluster, we have to look up in the Gluster namespace where that file is located, or where those blocks for that file are located. So that's an example of where we had to override the method and put some extensions in for Gluster. But you end up with a very tidy piece of code that's built off of a piece of code that's very well supported by the Hadoop community. So that's how we did our implementation and why it was effectively so easy to do. If you do some contrasting of HDFS and GlusterFS, so I've already mentioned that HDFS is a master-slave architecture. We're a peer-to-peer, no master-slave. In HDFS, you can pretty much only access the data via the HDFS API. And if there were a real strong Hadoop crowd here, they might want to quibble with that a little bit because it's technically not 100% true. There is both an NFS plugin and a Fuse plugin that's for HDFS that both are usable with limitations. So there are, the NFS plugin for HDFS is read-only today. So you'd have no write access. And the Fuse one is, I wouldn't say it's not commonly used. There's quite a few bug reports and stuff out on the big top bug reporting list about how some issues with the Fuse interface itself, so it's not super well tested, but it does exist. So anyway, predominantly you would access your data in HDFS through the Hadoop file system API. Gluster supports all those protocols I rattled off earlier, NFS, etc. In HDFS, and this is a really critical difference, data is not stored as a file. So if you ingest a file into HDFS, it's not stored as a file. It's broken into blocks. The blocks are persisted as files, but those blocks are scattered around the cluster. And so you can't, if you go underneath the HDFS API and just look at the raw data, you can't recognize the data you ingested because it's been broken into a bunch of partition files and scattered about. If you want to get back to the view, your view of the data when you ingested it, you have to go through the HDFS API. Is it? It does, and I'll talk some about it. But it's a perfect, shows that this actually is making some sense because that is a limitation in our current, on the right-hand side, in our current Gluster, file is stored as a file. That means it's only if it's a large file and it has lots of logical blocks, they're all on the same two servers. You know, the server 1 and 2, it's replication pair. So when you go to schedule a job, all the input splitting will work totally rationally. However, the hints that go back to the scheduler as to which nodes you can schedule this job on with data locality are limited because a large file is really only in 2 places in a Gluster cluster, whereas the fragments of the file are spread all over the cluster. So where it affects our implementation is you'll have fewer scheduling targets that are optimal when running the job. It doesn't cause a job not to run, but it could cause a job to not run optimally. Does that make sense? So it's correct. Metadata, centralized metadata approach versus limited metadata. I mean, the Gluster architects like to claim there is no metadata for Gluster, but that kind of makes my head hurt. There is metadata, it's just in the extended attributes. There's not a kind of separately maintained repository of metadata, but there is metadata, it's in this extended attributes area. That means metadata operations in HDFS are relatively inexpensive because there's a database, you just change the entry in the database. They're inexpensive, but they're centralized, so therefore a lot of metadata activity is hitting the same node, and that is not horizontally scaled. So I would argue they're inexpensive, but can still become a bottleneck at large scale because of the fact that the metadata server itself is not clustered except in the HA sense. On Gluster, metadata operations are relatively expensive because, as I mentioned, you have to maintain the consistent directory structure on all nodes, whether they have the file or not, with the extended attribute hints. So metadata operations, by comparison, are more expensive, but they are distributed. So replication is different. So if you're talking replication of data, not metadata, it's different. In HDFS, data is eventually consistent. So if you're updating a block, they will not, with every update all the replicas of the block. They will hit barriers, basically, which are either when they're a close or when somebody calls an hsync or an hflush to force a barrier. So the replicas are not necessarily strictly consistent with the one you happen to be writing to in a job. So that makes their replication of data lower overhead than ours in Gluster. Our replication translator is strictly consistent. And so those are a few examples of how being a more general purpose storage server versus something purpose-built only for an HDFS workload, we have to carry around full POSIX semantics, so we have to force more strict consistency on data operations and deal with more complexity, so that shows up as some differences here and there. Does that make sense? So a few observations. HDFS is purpose-built for running MapReduce workloads, and for that it's very well suited. So I'm a fan, actually. I think it's a good solution. GlusterFS is a more rounded general purpose storage solution with POSIX support and works with all your tools without no muss, no fuss. You can VI, you can grep, you can sed, you can awk, you can Perl, you can Python, any data. If the data's been ingested into HDFS, that list of tools is limited to tools that use the HDFS API. So it does not work no muss, no fuss with everything. Gluster trades some ultimate scalability for that flexibility that showed up in some of the stuff we talked about. Hadoop Job Performance is typically in the 0 to 25% slower than HDFS. Now there's a lot of variables in that. So, and I was hoping to come with some performance charts. However, we discovered some issues, just not a big issue, but an annoying little issue just last week that's throwing away some of our performance. So I didn't want to publish something and then have it be 10% better in a week. And so we will put out some more performance numbers when we're more happy with them. But they're kind of in that 0 to 25% slower range across things. I'll talk a little bit more about this in a minute. And typically, the hardware to run Hadoop would be optimized a little bit different than the hardware to run HDF. To run Hadoop, you would optimize it a little different than the hardware to run Gluster, a pure Gluster storage server. since Hadoop is going to host the compute layer always, or HDFS is designed to always host the compute layer, they pick a server that's more well suited to do both computation and storage. So you'd rarely see Hadoop deployed in a dedicated Hadoop cluster on something with 25 to 50 storage spindles per 2 sockets, whereas that's a common configuration for Gluster because Gluster is typically more of a storage server. Does that make sense? On the Hadoop, I already said this part about the Hadoop job performance. When I make that statement, that's sort of across a mix of high bench and workloads plus YCSB is the dashboard we're trying to track. The goal would be to get that for GA for our Red Hat storage product to within 15%, which customer feedback is that's a completely acceptable overhead to the kinds of customers we're targeting. We're not publishing exact numbers today. There are some subtle differences in the way the systems behave. For example, because of the centralized name node server, it's become a best practice in Hadoop to take lots of little files and merge them into one big file for processing. So like, it makes total sense in a Hadoop system to take log files from a zillion servers and their time series data. So use Flume or FluentD or something and merge those into a giant log file because that means there's only one metadata entry in the name node server, less metadata overhead in the name node server helps Hadoop scaling, and Hadoop's perfectly comfortable with processing a large file like that. That kind of hurts you in Gluster because that large file is only going to be put on 2 nodes, and so that becomes kind of a hard to hit scheduling target for the scheduler. So a better practice would be to not necessarily merge your data for processing on Hadoop. Now the jobs will run, like I said earlier, but the performance will come out a little bit different. And from a futures point of view, we will ultimately put out a version that does the blocking so that we don't have this issue that we're talking about, so we can do blocking inside of Gluster to a little bit smoother, more optimized performance. And today, Gluster, the Hadoop plugin goes through the Fuse interface, which puts quite a bit of overhead on an individual I/O path. And so turns out that doesn't really hurt us too much in Hadoop because up in the Java layer at the bottom of the Hadoop stack, we're doing buffering. So a large number of Hadoop reads or writes are buffered together before going into Fuse and traversing the stack. So we don't cross the Fuse from user space to kernel space and then kernel back to user and then into Gluster and then back into kernel. We don't go across that path as often as we would if we didn't do the buffering. So the buffering prevents the fact that we're through Fuse from causing serious performance overhead, but nevertheless, in the future, when we move to using libgf API, the native interface, we'll get some performance improvement. So for Red Hat, I put this in here because I want to make this point. It's like trying to say Gluster versus HDFS, like we want to displace HDFS or something. That's not a goal for Red Hat. I mean, I've already highlighted several places where HDFS is an excellent purpose-built file system for its intended use. Kind of a funny story is a little over a year ago, the Register, who loves to try to stir up trouble, put out an article saying that Red Hat was intending to kick HDFS to the curb and displace it with Gluster. And we were sitting in a room with a bunch of HDFS committers when the article hit the wire, and we all had kind of a laugh about it because we were working on a collaboration while there was an article in the Register saying we were trying to displace HDFS, and we're not. We're really more about having Red Hat be a good companion storage for Hadoop, not displace, and I'll talk about that in a second. And to that end, we've made contributions to something called actually we started it, the Hadoop HCFS, Hadoop-compatible file system, Apache. It's not really a project, it's kind of it hangs off of the Hadoop project, but it's to define tests and so forth for what are the semantics of the Hadoop file system so that if you're trying to create something that's compatible with file system, there are good tests for evaluating what the semantics are supposed to be. And this is actually valuable just to the HDFS community itself because they run into debates occasionally amongst themselves about, well, does this, recently there was a big brouhaha about what impact it would have to introduce symbolic links, and there weren't test cases for what symbolic links did in certain APIs and stuff like that. So the test for what are the semantics of the APIs actually helps HDFS itself. The two use cases for the plugin are really, this is kind of my way of saying it, and I'm not a marketing guy, but this is my way of saying it, is if you're more of a trailing edge adopter of Hadoop, so you haven't got some giant Hadoop cluster yet, but you're investigating it, this is a good place for you to store your data and then develop Hadoop jobs to explore that data and run the Hadoop jobs and learn a good way to get started with Hadoop. So it's a good entree into using Hadoop to analyze your data. Conversely, if you are more of a leading edge adopter and you already have a big Hadoop cluster, you're not going to take all your data out of your Hadoop cluster and put it in Gluster. It makes no sense to do that. The HDFS cluster is very well suited for that. However, pretty much all data that exists in HDFS usually exists someplace else in some other storage repository as well. And it's often pre-processed and before ingesting it into HDFS. So they'll change the format of the data or which fields are in the data or take certain data out for privacy reasons or stuff like that before putting it in HDFS. And this gives you a place that you can check out your Hadoop jobs against that data and make sure they're all working correctly and test and dev them before moving them into HDFS. So I call that the companion storage solution for Hadoop. So those are the two primary use cases. If you're attending Red Hat Summit, two people from my team plus Jacob Schukart, which is one of the Red Hat Storage SAs, is going to do a talk on customer applications of Hadoop on Red Hat Storage. So we'll be talking about a movie studio that's using Red Hat Storage to process log files, using Hadoop on Red Hat Storage to process log files. So let's shift gears a little bit. I got a couple more minutes. So where do we think Hadoop is going? Or where do I think Hadoop is going, at least? And I'm not going to try to go through this in gory detail, but kind of in the beginning, we had MapReduce and HDFS both implemented kind of in response to the published papers from Google on the Google file system and the Google MapReduce, and that kind of gave birth to the whole Hadoop project. And in the beginning, you had, it's kind of very fundamental to the Hadoop architecture that what you're trying to do is move the compute to the data. So you combine the storage and compute tools and you move the compute to the data to avoid the latency overhead of trying to read the data remotely over a network. And you know, Hadoop's a good 10 years old in terms of its birth. And 10 years ago, gigabit Ethernet was not even ubiquitous. So, you know, networking was much slower and both bandwidth and latency much worse. So the penalty for non-local reads was much higher relative to what local reads than it is today. So if you look at the trajectory, networks are getting faster, memory is getting faster, the rate of improvement of disk performance is fairly flat. The benefits of moving compute to the data are kind of unarguably lessening. There's still a benefit, but they're not as big a benefit. Secondly, when you move compute to data in Hadoop, you get this idea that you're getting a panacea that every job will read its data locally, but that's not reality. Hadoop clusters are overpressured. The scheduling problem is an NP-complete computer science problem. They always have to make trade-off decisions. Often jobs are scheduled against suboptimal locations, and in practice, Hadoop clusters see locality is in the 40 to 50% range oftentimes. So you don't even get all the locality by moving compute to data that was originally, that you might get otherwise. So there's a couple of trends working against that architecture, in my opinion. Hadoop at the same time is becoming much more general. So they've, the changes to the HDFS layer are pretty minor in nature, but they've changed it so MapReduce is now just a runtime that runs against HDFS, not the runtime. And they've introduced an abstraction layer in here called Yarn, which is a resource manager, which allows you to run multiple different types of workloads. So it's kind of generalizing as a framework, not just a MapReduce framework. And Oh, that's a bad choice of black on that color. Anyway, if you think about different types of workloads, there's batch workloads. This is historically the strength of Hadoop. If you want to explore a huge amount of unstructured data, you don't necessarily need the answer immediately, but you want to be able to find some relationship in the data that this is by far that you're not even sure if it exists, test some hypothesis or something. Hadoop is a pervasive way of doing that kind of data exploration. But these are not things, those relationships will not be discovered in seconds. The Hadoop jobs will take minutes or maybe hours to run, or worse. So there's a bunch of people that are interested in doing analytics with where they need the answer much more quickly. They need more like interactive query performance. They want to do analytics on data as it streams from some source where they have no hope of actually storing all the data. They want to be able to look at the data as it streams in and throw some and know that they've seen it before, or they've accounted for its effect on the calculus that they're doing already, so they can throw the data away and not store it. And there's increasingly a need to do deep learning and quantitative analysis on the data, which it can be done with Hadoop and the Mahout libraries, but it's complicated and it's not for the faint of heart, let's put it that way. So in my opinion, these are the areas where you're going to see a lot of work in the future, is on interactive query streaming and quantitative analysis. That's not a big, bold prediction. It's already happening. So as I mentioned, I think there's another more fundamental shift happening, which is we're moving from compute. There's a number of things that would suggest, including trying to explore those areas where there are kind of unmet needs or poorly met needs with Hadoop, to exploring an alternative architecture where instead of combining the compute and data layers, you separate the compute and data layers. You define a lazy mapping scheme for how this data set that you want to explore should fit into the distributed memory of a few nodes in a separate compute cluster. And then when you launch the job, you essentially copy on read the data into the separate compute cluster, but you're guaranteed you get the locality, and in fact you're going to run out of in-memory instead of any disk latency at all. So there's two very popular, or more, very popular frameworks that are emerging that move away from the MapReduce scheme to more of a separate compute and data scheme. One is called Spark, which is part of the underlying one of the underpinning layers of the Berkeley data analytics stack, and another is called Hexadata, which is kind of a narrowly provisioned, or not narrowly provisioned, but it's a narrower solution. It doesn't try to attack all those different workloads, but it focuses just on the quantitative analysis machine learning one. So I'm making the prediction that this is really kind of the way to go, because it's much more consistent with the hardware trends, and it opens up these other workloads for big data. And again, that's not a super bold prediction, because we already see all of the Hadoop distributors are already announcing support for Spark in their distributions and or starting to contribute to Spark itself. So, so the two leading examples, are Spark from BDAS and Hexadata of in-memory analytics solutions. They're not strictly competing in philosophy with Hadoop. So it's not really a black and white either or thing. Both of Spark and Hexadata support co-deployment, so you could put them on. They don't have to be in a separate compute cluster. You could put the Spark or Hexadata layers right on top of the HDFS layer. So they support co-deployment, and in fact, that's a popular way for people that have already, for customers that have already deployed a Hadoop solution, and so they already have procured the hardware. They already have it. If they want to check out Spark or check out Hexadata, they will often just co-deploy it on the hardware they've got rather than having a separate compute pool. So I would argue it's probably more optimal in a separate compute pool, but it's a perfectly reasonable way to deploy it, and a way that is easier in the sales cycle if you're selling to somebody that's already got a Hadoop cluster. So they're both positioned as complementing, not replacing Hadoop, and I would argue that's a critical success factor, because the truth is Hadoop has become incredibly popular. It has a giant ecosystem of partners and stuff that are developing around Hadoop, and a huge community of developers that are developing on the technology itself, and a huge amount of customer interest. So the last thing you would want to do is bet on a horse that is trying to compete with Hadoop. What you want to do is bet on horses that are designed to complement and round out Hadoop. And that's what these two in-memory technologies are examples of. And I would also argue they're kind of similar to Hive and Pig in the sense that part of the reason why Hive and Pig, which are very popular parts of the Hadoop ecosystem, have caught on so much is they make Hadoop more approachable. They provide easier language abstractions that are, so Hive provides you SQL-like language for accessing your data in Hadoop, and Pig gives you a language that looks more familiar and is more of a scripting language, more like Python. Shark adds first-class support for Python and Scala. So again, it's widening the audience that can develop. And Shark also adds, or Spark also, or BDAS also adds the Shark and Blink DB layers, which make the whole query access, if you like to query your data versus SQL, work better and have much higher performance. And then Hexadata embraces R and Python, which would be preferred languages of people that want to do data science. Most data science people don't want to learn a new language, and they already are conversant in those. So they're kind of riding the same kind of wave that drove adoption of Pig and Hive is another reason why I think they're going to be really popular. I think they have some big architectural advantages because they expand the number of applicable use cases you can tackle with big data. They significantly expand the developer bases by being more polyglot and embracing more developer communities. They fit much better with a cloud architecture, which I'll mention again in a minute. And they separate the management domains for compute and storage, which I would argue is much more optimal for capacity planning and cost optimization. So, so anybody that's been paying attention would notice that all public cloud services or private cloud services are the same in the sense that they offer one or more persistent storage solutions, like object storage or block storage or maybe file storage, and then a separate mechanism for elastically managing compute. So every popular cloud solution, whether it's for deploying something on-premise or in a public cloud, separates compute and data. Yet Hadoop is a perfect use case for deploying in a cloud because it's horizontally scalable architecture, et cetera. Hadoop wants the data and compute tiers combined. All the clouds separate the compute and data tiers. So Amazon wrote something called Elastic MapReduce, and we've, in conjunction with Mirantis and Hortonworks, have created the Sahara project in OpenStack to schedule and provision Hadoop clusters in OpenStack. So sure, we have ways of orchestrating the deployment of Hadoop in a cloud, but they're kind of fighting the existing architecture because you either end up having to, you're always going to end up having to read the data out of a separate repository because no cloud allows you to run the compute on the data, a la the Hadoop architecture. So my point is that these new in-memory compute paradigms fit much more naturally with all the cloud architectures, and that's going to be another one of the driving forces. Does that make sense? And then from a capacity planning point of view, because we've put compute and data together in Hadoop, that means you have to decide, you have to manage the capacity of the compute and data tiers together. You've tied them together, which means you can't manage them as separate concerns. So the things that drive storage growth are different than the things that drive compute growth. My argument is compute is somewhat elastic. You know, you're going to want to process your data. Some event will occur, it will produce new data. Some other event is going to happen in time where you need some analytics against that data that was just produced in order to draw some conclusion and take advantage of it. So it's temporal in nature. And the things that drive the need for computing may line up. So you get big spikes in when you need computing power and then troughs. And if you have a static compute resource versus a flexible compute resources, you can't really match your capacity to your capability to your demand. So on the other hand, so compute demand goes like this and basically increases in a step function. And storage demand is just an exponential curve. So tying the two together means you've got two different capacity planning domains that you've had to manage together. So that's another strong factor. So back to the premise for my talk, what we've done for scalable storage for big data is we've created an excellent Hadoop plugin for Gluster, which allows Gluster to satisfy the use cases I mentioned. Hadoop is a very, HDFS itself is an excellent storage mechanism for MapReduce, but my argument is that is going to decreasingly be the dominant workload of the future. Increasingly, some of these other workloads, you're going to more see a separation of compute and data in the future, which will decrease the need for a single storage domain to be massive and increase the applicability of other storage domains. So when you're looking at the scaling question today in a Hadoop, it's nice that a Hadoop HDFS proves it can scale to 1,000 or 4,000 nodes because it has in practice. But if you separate the compute and storage tiers, you have far less of a need to scale to that large of a single node count. So that's my, my conclusions, basically. We believe there's big changes in the way big data is going to be processed. We're bullish on future technologies such as Spark and Hexadata. There's a growing focus at Red Hat on ensuring that OpenStack itself is an ideal platform for big data processing. Matt, sitting in the audience right here in the green shirt, is doing a talk Wednesday from 3:40 to 4:40 on our Sahara, which is our mechanism for doing elastic provisioning of Hadoop clusters in an OpenStack framework, so you can catch that. That's a DevNation talk. The other talk I referenced on customer use of Red Hat storage with Hadoop is in the Red Hat Summit track, so I don't know if all of you are also registered for both tracks, but it's in there. So that's it. We don't have a whole lot of time left, but if anybody has any questions, I'd be happy to take them. So.